Okay, thank you very much for the kind introduction. And yes, this is a new topic, so it's no longer perovskite silicon, but all-perovskite tandems, as investigated, for instance, in the Super Tandem project. So why should we look into this technology? So all-perovskite tandems are scalable and flexible technology that have already demonstrated also very high efficiencies. But when scaling up these devices, there are of course issues when using large area deposition, especially spatial non-uniformity in material quality as detected with various characterization methods. And another issue that you always face when you have module integration is the issue of partial shading, especially reverse bias that you have on the shaded cell. So now for perovskite, the dissipation of power can be quite an issue, especially if it's happening localized, so if you have a hotspot. And in perovskite, you have the additional situation that under reverse bias condition, the mobile ions, well, they screen the field inside the perovskite, but they actually increase the field close to the contacts, and then this can promote this tunneling breakdown via the Zener mechanism. Sorry. Wrong way. Okay, so in fact, it's interesting to observe that this reverse bias breakdown depends not only on the type of perovskite, but also on the specific architecture, especially the choice of charge transport layer used. So in tandems, we have the additional complication that the limiting subcell is reverse biased already at, well, moderate forward bias or short circuit. So you have already a high field in this situation before even going to reverse conditions for the full cell. And then also in all-perovskite tandems, I mean, these are the same kind of thin film large area devices. There is non-uniform material quality, and this can of course also affect the distribution of mobile ions that have then an impact on the reverse bias breakdown. So in this presentation, I want to look into the role of mobile ions in reverse bias breakdown in these devices on cell level, and then propagate this to study the impact of spatial fluctuations, both in interface passivation and mobile ion concentration on the operation of all-perovskite tandem modules, so both in the forward bias conditions, but also in the reverse bias regime, to see whether we can have this hotspot formation due to these non-uniformities. So for this, I use a multi-scale approach. So I need a model level simulation, which is this kind of quasi 3D approach, where we have 2D finite element resolution of the electrodes, and then we have the scribes implemented via sheet resistance values for the P1 and P3, while the P2 scribe is just an ohmic coupling between these two electrodes. And then the active area, well, for the TCO resistance losses, you have again the sheet resistances, but for the coupling here in the active area, you use the JV curves of small area solar cells. And now, if you have, well, these spatial fluctuations, you need, of course, spatial resolution. So we have these small area solar cell JV curves for each pixel here. So under illumination, you need just the forward JV curve, but if you have shaded pixels, you also need both the dark and the reverse regime for dark and illuminated. So you have to get first these JV curves for both forward and reverse bias regime. For this, we used then a cell level simulation, and this model I presented actually last year at this conference. So it's based on a published structure from TU Eindhoven of this all-perovskite tandem, and the model is implemented in our device simulation tool ZFOS. So it's the usual combination of optical simulation using transfer matrix with the drift diffusion level electrical simulation, where it's important to include mobile ions. So this model was calibrated using a wide range of different experiments. And then the first thing I looked at was the effect of interface passivation. So in this case, we have device performance that is limited by interface recombination between the perovskite absorbers and electron transport layers. And by changing interface recombination velocity over 4 orders of magnitude, you have like a 7% absolute PC difference around an average device quality. So this gives you this distribution of JV curves here. Now for the reverse bias regime investigation, we also start from the device level simulation with drift diffusion. But then we need to couple this to a quantum transport simulation for the breakdown in these high field regions here. So actually this resolves the whole contact region, so it's not really limited to a single material. But doing the simulation, we see that actually the breakdown occurs not in the perovskite itself, but in the C60 charge transport layer. Then when we have these tunnel currents, we can extract the recombination, or let's say in this case tunnel generation rates that we feed back to ZFOS, to the drift diffusion, and we do that self-consistently, so until we have a converged solution for the reverse JV characteristics. So this is then the result for the top cell. So now first I want to look at the relatively low density of mobile ions and see the impact of the photo-generated carriers, because we also need the device characteristics under illumination. In the case of partial shading, a part of the cell is actually still illuminated. And what you see is actually that the photo-generated charge carrier density changes also the field in this breakdown region, and this changes the tunnel current and leads to an apparent photocurrent gain. So you have a deviation from the superposition of the dark current and the short circuit current here. Now, if I increase the density of mobile ions, the field becomes much stronger, and this reduces strongly the breakdown voltage. So I have breakdown much earlier, and in this situation, the mobile ions dominate over the photo generation. The situation is similar for the bottom cell, just that here the effect of the photo generation is not really visible, and since we have lower mobile ion density, we also have a smaller reduction of the breakdown voltage. What is interesting to see here is that actually, even though this is a smaller band gap of the perovskite, the breakdown voltage is larger. So this is just another consequence of the fact that the breakdown does not occur in the perovskite, but in the charge transport layer. So now we can construct the reverse JV characteristics here, and we have basically two regimes in reverse bias to look at. So the first is when the top cell is still forward biased, but the bottom cell is already quite deep in reverse. So this I call the shunt regime, because basically it's determined by this shunt resistance in the bottom cell. The second regime is then the breakdown regime, where both the subcells are at breakdown. So we then compute these characteristics for different concentration of mobile ions, and we see that the shunt regime is not really affected as expected, but we have a very strong impact of mobile ion density on the breakdown voltage, both in the dark and under illumination. So now we propagate this to the module level using this calibrated module simulation. So this was also presented last year. This is a simulation based on All-Perovskite Tandem module of EMPA. And first we look at interface passivation, and now we randomly attribute to each pixel a curve from a Gaussian distribution of interface passivation quality, as shown before. We see that now indeed the source power is dominated by this strong fluctuation of the small cell efficiency. However, if we look at the large area cell and the module level, we see barely a deviation from the reference performance. So on the forward bias, there seems to be robust behavior. Now if we go to the reverse bias situation under partial shading, we do the same attribution of spatially random attribution from a Gaussian distribution, but now we take that from the distribution of reverse JV curves here. And first we look at the fully shaded cell case with a uniform density of mobile ions. And we start with the lowest concentration of mobile ions. So in this case, we have a severe degradation of the performance as expected, and we have a very large reverse bias here on this shaded cell. But the current is, while it's low, it's uniform. So we don't see any hotspot or any non-uniformity that would be dangerous. If we go to a higher concentration, actually the maximum power point is not degraded that much because the breakdown voltage is actually lower. So we have a lower reverse voltage here, and the current map now looks very similar to the one under forward bias. Things actually become more interesting when you now allow for fluctuation of the mobile ion concentration. So the behavior looks like an average one, so you have an average degradation. In the forward regime, it's not really very well visible. You have quite, also an average reverse voltage here. If you now look at the current, the situation is quite drastically changed because you have now the appearance of these hot spots. So the average current is quite low, but then you have some pixels where you have an extremely high current. If you have partial shading, your maximum power point is at a quite high voltage, and this means that you're not in the reverse breakdown regime here, you're more in the shunt regime. And in this situation, you have almost no current here, so in the shaded part, they have no current, and all of the current flows here in the illuminated part, but the current flow is uniform. Now, if you go to a point that is not the maximum power point, but you have a larger current, well, the voltage is lower, and you go back to the reverse breakdown regime, and again, you have these hotspots. Now the hotspots are most pronounced in the illuminated part here. Okay, this brings me to the summary. I presented this multi-scale simulation approach to investigate interface passivation and reverse bias breakdown in all-perovskite tandem solar cells. And this allows you to quantify the impact of the interface recombination velocity or passivation quality, but most importantly, the mobile ion density on forward and reverse tandem characteristics on device level. And this can then be used on module level to look into the situation, which appear to be robust at maximum power point, even for large uniformity of interface passivation. But in the reverse, under partial shading conditions, you see the appearance of these localized current hotspots due to this spatial fluctuation of mobile ion density. So most of these results you can read in this paper that appeared this week. And I would like to thank my colleagues at Fluxim, the funding bodies, and you for your kind attention.
Thanks very much. I think we have time for a quick question, if there are any.
Urs Aeberhard from Total Energies. Reverse bias characteristics and partial shading tolerance is a very hot topic for us to understand. I believe to have understood that you approach that from the point of view of simulation only and not necessarily as a material scientist, right? Nevertheless, would you be daring to comment on whether you can keep the perovskite cell alive if you provide that every part of it remains in what you call the shunted regime before the breakthrough happens?
Yes, this is of course the obvious question. This is more the physicist's approach, assuming that the material doesn't change. But yeah, there are studies that show that exactly this happens. So you have some chemical reactions happening under these large field conditions, which can introduce additional shunting paths, additional mechanisms that you don't have this exponential breakdown curve, but you have like a sudden death or, so I guess the picture might be much more complicated. However, there are measurements, they look like this, and this is very close to what we simulate. So this is an actual device that was measured. So it seems to be possible that you find this behavior. But we tried to measure it for single junction, and it's very difficult to find reproducible data. I also saw data from other labs. I mean, always with mobile ions. Now there is a history. Once you measure, next time it's a different device. So yeah, I think this makes it very difficult to find a, let's say, experimental basis to validate. So this is the scenario of the clean physics, I would say. Yeah.